Hey folks, Dr. G here with a lesson on deriving the canonical ensemble from spin states. Now, the canonical ensemble is a really important concept in the field of statistical mechanics, sometimes called statistical physics, which is a really important field in both physical chemistry and condensed matter physics. And today we are going to derive that expression for ourselves, starting with just simple coin flips. So here is an example of a two-state object, right? A coin. It's either heads or tails, or in the case of the coin on the screen here, it's either the blue side up or the white side up if we were to flip that coin. And of course, we just talked about two-state systems in my video on absolute negative temperature. So if you haven't seen that yet, I recommend that you actually watch that first, because this video builds on some of the concepts that are covered in that video. Another video that may be of interest to you is the video you see to the left there, where you see a younger version of myself flipping coins there. So I recommend you check that one out as well. It deals with the third law of thermodynamics, and it also works with these two-state systems. Now, for today's lesson, I want you to consider a set of 4 coins like this, these 4 blue and white coins. And let's say that I shake them on my hand and I throw them on the table, and then we count how many are blue side up versus how many are white side up. Also, I want you to consider these coins to be indistinguishable, meaning we can't tell one coin from the next, right? We're shaking them in our hand, and once we throw them on the table, we don't know which one is which. And so given this set of indistinguishable coins, we want to be able to study the statistics of how they behave, i.e. how many states can we observe and how likely is each state? For example, we can have all of the coins land blue side up, or half of them land blue side up, half white side up, etc. So we want to determine what the statistics are of these different states occurring for these 4 indistinguishable coins. Now, obviously, there's only one way to get all blue or all white, right? There's no other way we could sort of reconfigure that to get all blue or all white. So there's only one way to get all blue, one way to get all white. And if we look at the case where you have 3 blue and 1 white, or 3 white and 1 blue, it's the same for both. There's 4 ways you could do that. So basically it's 4 choose 1. You have to choose one of the coins that's going to be different from the others. So there's 4 ways to get each of those cases. And now if we look at the case where we have 2 white and 2 blue, well, there's 6 ways to do that. And I've enumerated all the different ways at the bottom there, where we can have 2 of them white and 2 of them blue. So if I ask you which case is the most likely one to see, your intuition is probably going to be correct, half blue and half white. And that's true. That is the case we're most likely to see for these 4 coins. In fact, for any set of coins like this, half blue and half white is what we're most likely to see. And for larger and larger sets of coins, that gets more and more dominant. So we know the number of ways, but how do we turn that into a probability? Well, the way we do that is first we have to add up all the number of ways that we can get any of the states, right? So you just add 1 plus 1 plus 4 plus 4 plus 6, right? We've added all of these ways together, we get the number 16. So given a system where we know the number of ways to get each possible state, and we've added them all together so that we know all the number of ways that it can be configured in any way. If we know all of this, then the probability of one of these states being the outcome is simply the number of ways to configure the state of interest divided by the total number of ways to configure the system in general. Thus, for the system at hand, if we divide the number of ways for each state by the total number of ways, 16, now we have probabilities. Now, the important thing to acknowledge about this system here, the blue state and the white state for any individual coin is equally likely, right? So this way of calculating probabilities will work as long as the individual systems are equally likely to be blue or white. And in the case of a fair coin, yeah, that's true. 50% heads, 50% tails. Now, what if we had an unfair coin, right? Let's say, for example, each flip has a 75% chance of being blue. Right, this is not a fair coin now. Well, now what happens? This is going to be a little different. But instead of continuing our discussion with coins, let's talk about something relative to physics and physical chemistry. All right, let's talk about spins in an external magnetic field. So now, for our two-state system, we have a 75% chance that any particular spin is going to be aligned with the magnet, and a 25% chance that it's going to be anti-aligned, so like fighting the magnet. So given a system like this, we have an external magnetic field that is trying to align the spins. Well, If we think back to the negative absolute temperature video, we learned that heat applies random kicks, right? And the hotter things are, the harder the kicks are, but the direction is random, right? It could kick it so that it stays aligned with the magnet, or it could kick it so that it fights against the magnet, right? It doesn't prefer one direction over the other. So the fact that some of these spins can go against the magnet, that seems to imply that there's some sort of energy source that's providing energy to the system. Now, there are different conditions under which we can think of the system having energy available to it to flip spins against the external magnetic field. One of the simplest ways for this to be the case is, what if we have an adiabatic system that some energy has been let into the system in the form of heat, and then it's closed off to the rest of the world, right? No heat gets in or out, no spins get in or out, right? Everything's trapped in the adiabatic system. Well, that's one way this could happen. And then basically the total energy of the system would have to stay constant, right? Because nothing can get in or out. There is a statistical mechanical treatment for such a system, and it's called the microcanonical ensemble. But today we're going to be talking about the canonical ensemble. And for the canonical ensemble, what happens is that our system is in contact with a heat bath. Right? So if you've ever taken a chemistry lab where you run a reaction, and maybe you have a round bottom flask that is running a reaction and it is in an oil bath that's set to some particular temperature, right? Then there's energy can go in and out of your system, right? It is not adiabatic, but you're running at constant temperature. That's the sort of system we're talking about today. And basically the bath is considered incredibly massive compared to the system itself. For example, consider a cold-blooded fish that lives in the ocean. The ocean is going to set the temperature for the fish, right? And if the fish starts swimming vigorously, right, it's doing work with its muscles. Well, you can't do any work without producing heat, right? The second law tells us this. And if the fish starts swimming vigorously like that, yeah, it is going to give off some energy, right? Some heat is going to leave the fish, but the temperature of the ocean's not going to change, right? It's just like the Weather Channel isn't going to update the water temperatures because you went swimming that day, right? It's not enough to change it. So this is the idea of a reservoir versus our system, right? So this is what we're thinking about with our bath, is that we have this massive bath that can hold our system at a constant temperature, but not at a constant energy, right? Energy can go in and out of our system, and it's supplied by the bath. So because energy can go in and out of our system, then our system has some probability of being in any of its possible states. And unlike the coin flips, where the number of ways determines everything, right? There's actually two things that contribute to the probability of a particular state here. The number of ways is definitely still a factor, but also we have the joint probability of these spins being in a particular state. So as I said, right, these spins for our particular example are 75% chance aligned and 25% chance anti-aligned. Now, since the coin flips already told us how many ways we can get to different configurations, right? This is still a two-state system. The number of ways is going to stay the same. So let's go work on the joint probabilities. Now, I've just arbitrarily named all the different states, right? Just going from left to right, state 1 through state 5. So if we look at state 1, there is a 75% chance that a particular spin will be aligned with the system. And in this particular state, they're all aligned. And the way you get joint probabilities is that you multiply them together, and the product of all of these individual probabilities gives you the joint probability. One thing to bear in mind about joint probabilities is that the assumption is that they're not affecting each other, right? And that is the case with our spin system here, right? These are independent spins. They're all doing their own thing. So 3/4 times 3/4 times 3/4 times 3/4 gives us 81 over 256. So that's the joint probability of all of these 75% aligned spins being aligned. Let's calculate the other four now. State 2, where all of the spins are fighting the external field. We might think like, all right, this one's probably not a super likely one, and our intuition would be correct. In fact, 1/4 times 1/4 times 1/4 times 1/4, we get 1 out of 256. So this is obviously a much smaller joint probability. Then the joint probability of 3 aligned, 1 anti-aligned works out to 27 out of 256. Now looking at 3 anti-aligned and 1 aligned, we get 3 out of 256, so again a pretty small one. And then finally, if we look at half up, half down, we get 3/4 times 3/4 times 1/4 times 1/4, which is 9 out of 256. So this half up, half down state that really dominated for coins, we see that the joint probability at least is a good bit lower than some of the others. So those are the joint probabilities, not taking into account the number of ways that you can achieve each of those joint probabilities. So if we put the two together, we can say that the probability of one of the 5 possible 4-spin states occurring can now be calculated as the joint probability of each set of spins multiplied by the number of ways to configure that state of interest, all divided by the sum of all possible joint probabilities multiplied by each of its respective ways to configure that state. Now that's a lot of words, so let's write that as an equation instead. Much better. All right, so here we have an equation that says the exact same thing. And we see that the number of ways is W and then multiplied by our joint probability, right? So this is the abbreviation we've been using, where the J represents joint and the I represents which state we're in. Now, looking at the denominator here, this is actually a really important expression in the field of statistical mechanics, and it's called the partition function. For the canonical ensemble, we often abbreviate the partition function as Z, so we're going to call that Z. Now, let's take this expression for the probability of each state that takes into account both the number of ways and the joint probabilities, and let's calculate some of these probabilities. Well, the first thing we're going to want to do is calculate our partition function Z. So after adding it all up, we find that it comes out to Z equals 1. Now, we don't always get Z equals 1. This is just for this particular choice of 4 spins and that 75% aligned, 25% anti-aligned choice, right? So it just happened to be 1 here. There's nothing particular about that. Although one thing that's kind of nice is that, when we divide by Z, we're just dividing by 1. So let's look at 3 of the more interesting cases here. So the probability of state 1. State 1 is where none of the spins are fighting the external magnetic field. It's fully aligned. And we see that it's 31.6% of the time. And so this is, intuitively, this might surprise you a little bit that it's this low, right? Because this is the lowest energy state. It's not fighting the external field at all. But you can only achieve it one way. So we're seeing that we have some competing effects here between the number of ways to achieve the system and also the joint probabilities, given the probability of the spin being aligned or anti-aligned. Now state 3, where we have 1 fighting against the field and 3 of them aligned, we see this is the highest one at 42.2%. So this one, even though it's higher in energy than the fully aligned one, it's a good bit more probable that you'll see this state instead. And finally, we look at state 5, half up, half down. Now this is the one that dominates in coin flips, right? When the number of ways determines everything. But now we also have to worry about those joint probabilities, and we see that it really does penalize it a good bit. It's down to 21.1% when it was on the top when it came to coin flips. So now looking at this slide, we see all of the probabilities of all 5 potential states here. And we see that, look at state 2. So state 2, where all of the spins are fighting against the external field, we figured that one was going to be the least likely one, right? But look just how unlikely it is. It's 0.4% of the time. That's your probability of observing that state. So almost never. And also state 4, that probability is only 4.7%, where only one of the spins is going with the magnetic field. Now, notice when I put this together, I assigned higher probability to the aligned state than the anti-aligned state. And intuitively, this probably shouldn't surprise you, right? Of course, we're more likely to see the lower energy state. And this highlights a really important notion that the probability of a state is inversely related to its energy. So if you're thinking about an equilibrated system, well then the low energy states are the ones we are likely to see, and the high energy states are the ones we're less likely to see. Now, I'd like to point something out that was awfully convenient for me, right? I knew the probability of aligned versus anti-aligned. Right? This isn't something that you'll necessarily know in an experimental setup, right? This isn't something that's like necessarily easy to measure, right? We don't have like a probabilityometer, but we can measure energy. So our next goal in building the canonical ensemble for ourselves is we want to replace these joint probabilities with something we can actually measure. We need some function of energy that'll give us that joint probability. So similar to the negative absolute temperature video, we're going to define the energy for our 2 states here. We're going to say that if the spin is aligned, that's 0 microelectron volts. And if it's anti-aligned, that's 1 microelectron volt. Now, remember I made a big deal out of how the coins were indistinguishable. Well, if we think about a bunch of spins contributing energy, it's a similar thing, right? Maybe you can measure the total energy somehow, but you don't know which spins are contributing how much energy, right? You don't know the individual contributions. They're indistinguishable. And since we're working with this convenient system where the energy of each spin either contributes 0 or 1, it's very easy for us to calculate the energy of the system, right? You just add up the number of anti-aligned spins, and that's energy. So notice that I've written E equals 0, E equals 4, etc. below each state. So if we can find an expression that's in terms of energy instead of the joint probabilities, and we have the binomial coefficient expression that can give us the number of ways, since they're spins, it's one or the other, right? We will be able to calculate the probability of every possible state here using things we can actually know. So we're going to replace those joint probabilities, right? The P with the J above it. We're going to replace those with something measurable. It's going to be a function of energy. And since we're using energies in our expressions now, we should refer to the states by their energy instead of those arbitrary names I gave them before. So now the subscript is going to refer to the energy of the system. All right, so we need some kind of function we can plug energy into. So our function is going to need to have certain properties. For example, it should be monotonically decreasing, right? If I give two energies to this function, a lower one and a higher one, the lower energy needs to produce a higher probability every time, right? So we can't have the function going back and forth. It has to be monotonically decreasing. Also, negative probabilities don't have any meaning, right? There's no meaning to a negative probability. So we can't have our function returning a negative probability. So this function cannot go below the x-axis. And of course, normalization must be preserved, right? If we add the probability of every possible state, it needs to add to 1. But since we're applying this function we're going to choose, we're going to apply this function to both the numerator and every term in the denominator. So our normalization is going to be preserved. So here we have good old exponential decay, right? So we've got e to the minus beta x. What's beta? It's just a constant for now, right? We'll think of that as a parameter of our model here. But of course, just knowing about exponential functions, we know that if we put a large magnitude beta on this exponential, it's going to decay faster. So let's check for all these properties we said we would need. We need monotonically decreasing. Yeah, that function is just going to keep dropping as it goes to the right. So we're good there. Does it ever go negative? No, it does not, right? It asymptotically approaches the x-axis, but it's not going to go negative. Another important property here for our choice of function here for mapping energies to replace those joint probabilities from before is that they need to accept negative values for energy without breaking down. And we notice that, yes, this function continues in the negative x direction, and it keeps going up and up and up. As you give it a lower value for x in the negative direction, you're going to keep getting a higher value returned. And the reason for this is because energy is relative. Every energy is compared to some other energy. There's no absolute energy, right? We'll define things like a heat of formation or standard conditions, but somebody made those up, right? We conveniently choose them, of course, but every energy is relative to some other energy. Therefore, this function needs to be able to accommodate negative energy values. So let's try it out. Let's take these expressions on the left that have those joint probabilities and just replace those joint probability symbols with our exponential function, e to the minus beta times the energy of that particular state. And again, we have the expression for the partition function and the expression for the probability of a particular state occurring. So we know the number of ways to achieve each of these states, and we also know the energies, right? They're both very easy to count up. So we already know the number of ways to achieve each state, and we also know the energy of each state. So all we have to do is plug it into our expression here for the partition function. And when we do that and simplify a little bit, we have this expression here where we have some integers, we have the constant e, and we have beta. And at this point, what do we do with beta? Well, we haven't defined what beta is physically, but let's explore a little bit, right? Let's say we're not sure what that is, why don't we look at how it behaves at the limits, right? So what if we make it really small and then make it really big? We can try and intuit the meaning of beta. So as beta approaches 0, if I just plug a 0 in for beta there, we get 1 plus 4 plus 4 plus 6 equals 16. And then we can calculate the probabilities using our probability expression, 1 over 16, 4 over 16, 6 over 16, 4 over 16, 1 over 16. So looking at these probabilities, do they look familiar to you? Where have we seen these numbers before? Think about that. We've seen them before. Think to the very beginning. The spins are now behaving like coin flips. So if the spins are behaving like coin flips, they're basically ignoring the magnet. The spins are just, up, down, it's all random, right? The magnet is having no effect on the spins at this point. And so now think back to the absolute negative temperature video. When did we see the spins just completely ignoring the magnet? Well, that's as temperature approaches infinity. So this seems to be correlating with temperature going to infinity. So if beta approaching 0 starts behaving like temperature going to infinity, well, if we think about that, 1 over a really big number approaches 0. All right, so bear that in mind. Now let's look at it the other direction. Now let's think about beta approaching infinity. So now if I plug infinities in for all of those betas, well, it's e to the minus constant times infinity. Well, that makes those e's decay down to 0, doesn't it? So we're left with the probability of the system being in the 0 energy state being 100% chance. Everything else is now 0. Well, when are we guaranteed to be stuck in the 0 energy state? Absolute 0, right? We must be at absolute 0 now. That's what's going on here. So basically, we're seeing temperature going to 0. As temperature approaches 0, you are guaranteed that your spins are all going to be in that lowest energy state of everybody's aligned. So now we've shown for both beta approaching 0 and beta approaching infinity that this is definitely behaving like inverse temperature. So it's related to inverse temperature. That's almost the full answer. Inverse temperature is almost the full story, but not quite. And also, I mentioned that we were going to double check that our normalization is preserved, and sure enough it is, right? If you add 1 to a bunch of zeros, that's going to give you probability 1, and those other fractions, actually we've already added those up before, that's going to give you 16 over 16, which is equal to 1. So normalization is preserved. So we've proven that beta must be related to inverse temperature, 1 over t. But as I said, it's not quite the whole story, and look at that expression. Your hint is units. How do we know what the rest of beta is? Exponents must be unitless, right? If you have an exponent in an equation for a physical system, units need to cancel, right? You can have things in the exponent that have units, but they all need to cancel out. Exponents must be unitless, right? Because the Taylor series of an exponential function is a polynomial of increasing order, right? So if you think about length, right? If you have inches, and you have inches plus inches squared plus cubic inches, right? You're talking about adding volume to length, right? If I said, oh, how much gasoline did you get? Oh, give me a gallon plus 3 or 4 inches, right? That doesn't make any sense. You can't do that. So we know this exponent cannot have units. Therefore, we know that beta must be 1 over Boltzmann's constant times temperature. And why Boltzmann's constant? Well, Boltzmann's constant is, I like to think of it as the rate of exchange between energy and temperature, right? It's energy per temperature. So if you multiply Boltzmann's constant by a temperature, you're going to get energy. And of course, we have to have 1 over energy so that the energy in the exponent cancels. So our units do cancel now. And so now we have justified our expression e to the beta times energy. And you may have seen this before as the Boltzmann distribution. But in this lesson, we've justified it for ourselves. So this expression below the blue box, this is a very special thing in statistical mechanics. It is called the partition function for the canonical ensemble. And another way you might see it written is like this. This is simply another way to write it, where this function g, that's our degeneracy function, where you pass it an energy. You say, okay, for this state, how many ways can I achieve it? And that's what the degeneracy function does. And in the case of our spin system, we know what that g function is, right? It was that binomial coefficient expression that had all the factorials in it. And although we built up the canonical ensemble using a set of spins, this isn't limited to a set of spins, right? We can do this for any state where we have an ensemble of objects with discrete energy levels. For example, in many textbooks, you'll see the canonical ensemble for a system of quantum harmonic oscillators. I think it's also good to point out that the canonical ensemble is also not limited to quantum systems, right? You can have classical energy levels, right? Where any energy is allowed, right? That's the main difference here. In the quantum system, there's only certain allowed energies, right? You have discrete jumps, quantized jumps, makes it a quantum system. But in classical systems, it's continuous. You can have any energy you want. And we can still define a canonical ensemble for a classical system like this. And we see that another concept that I really love to talk about, that if you think about sums and integrals, they're related, right? An integral is like a continuous version of a sum, and a sum is like a discretized version of an integral. So we see that the classical representation is actually quite similar, right? You have to remember your differential dE, but other than that, it's pretty much the same deal. The classical expression for the canonical ensemble has the same basic form as the quantum version. So now that we have an expression that depends on the energy of the spin states, instead of just us, kind of magically knowing the probabilities of them, let's see if we can get that same system from before, right? Where we had 75% chance of being aligned, 25% chance of being anti-aligned. Let's see if we can find an energy expression for that now. So the way we're going to do this is we're going to look at a ratio of probabilities. This is also known as odds. Right? If you say, I give something 3-to-1 odds, something like that, right? We have the probability of one outcome divided by the probability of a different outcome. So for our case here in numerator, we have the probability of anti-aligned divided by the probability of aligned. And we're just going to look at a single spin here. Now, I want you to look at this expression here and notice the z's cancel out, right? Because z's the same. The partition function is always the same. And the reason I'm making such a big deal about this is that partition functions for most systems are very, very difficult to obtain. Obviously, I chose a system where we can get one pretty easily for teaching this concept, but it's actually usually very hard to get the partition function. So one trick that is very often used is to look at odds instead of probability, because this way the partition function cancels out. In fact, in a chemistry course, you may have been looking at odds without realizing it. If they talked about a relative population, that's odds. So if we take our probability expressions here for anti-aligned versus aligned, this is what we get, right? We're looking at just one spin. There's only one way to do this, right? So W is going to be 1, and you're going to have e to the minus beta 1 if it's fighting against the magnet, right? Anti-aligned, and 0 if it is aligned with the external field. And of course, our goal here was to look at the state that we looked at before that had a 25% chance of being anti-aligned with the external field. So on the left side of the equation, we have 0.25 divided by 0.75. And on the right side, we have e to the minus beta. And if we do a little algebra here to solve for beta, we find that beta is equal to minus 1.1 inverse microelectron volts, right? Because beta is 1 over energy. And since we have our value for beta now, we have everything we need to calculate the partition function, because we already knew the energies and we already knew the degeneracies, right? The W's, the ways of achieving the different states. We know everything now, so let's plug it all in. And we find that our partition function is equal to about 3.16. And if we plug this into our expression for the probabilities of each particular state, we see that, yeah, they do match the ones that we calculated before where we had to know the probabilities, right? Now we just know the energies, and we can still get the probability of each state. But we can even take it a step further and ask the question, well, okay, what temperature does the bath need to be for this particular system in order for a particular spin, any particular spin that we select, to have a 25% chance of being anti-aligned? All we need to do is plug in beta into our definition for what beta is and then solve for temperature. And we get the value 0.01 Kelvin. Now that's really cold. So just thinking pragmatically, is there something else we could do? Like, let's say we wanted our spins to have, again, this 25% chance of being anti-aligned. Is there something else we could do to the system? And, we can't change the strength of the dipoles, right? This is, for example, nuclei. Let's say they're protons. We can't change that. Is there something else we can change so that we don't have to go to 0.01 Kelvin? We're going to need a bigger magnet, right? We can't change the strength of the magnetic dipoles in the nuclei of the system we're studying, but what we can do is put it in the presence of a stronger magnetic field so that that difference, right, that difference in energy, the energy gap between being aligned and anti-aligned gets a lot larger. So this is why the resolution of NMR spectra improves for both lower temperature and higher external magnetic fields. More specifically, you want the probability of your spins being aligned with the magnet as high as possible, right? You want as few fighting the magnet as possible, because then when you do the population inversion, when you flip it, you get a more pronounced relaxation and a stronger signal. And I thought I would include a picture of this 900 megahertz magnet here for NMR spectroscopy. I think these things go for, I don't know, ballpark, maybe 4 or 5 million, something like that, right? So it takes a lot to get a magnet this strong. So with nothing but 4 spins and an external magnetic field, we've managed to derive the canonical ensemble. But again, I want to remind you that the canonical ensemble can be applied to any system, no matter how many energy levels there are, right? For the spin system, there's only 2 energy levels, right? But it could be a quantum harmonic oscillator with unlimited energy levels, right? You could do that. Also, it doesn't have to be discrete energy levels, right? The energy levels don't need to be quantized. You can do it for a classical system as well. So that brings us to the end of this lesson. I really hope you enjoyed it. I really love this topic, and it's my hope that this video helps many other people learn to love it as well. Well, I'm Dr. G, and I'll see you in the next video.